Okay, in this lesson we're going to start looking at exponential functions. And that is the graphs of the functions, as opposed to just dealing with the exponents themselves. We're going to start seeing what happens when we start graphing these functions. Okay, an exponential function is any equation that has the exponent as the unknown value. So up here, it has to have the x. Okay, and for now, our bases are always going to be just some sort of base and some sort of number, so b is called. So an example could be 2 to the x, or maybe it's going to be 1/3 in brackets to the x. Okay, those are our choices. Okay, exponential functions have a whole number base, so one like this, that's a whole number base. Okay, we are said to be growing functions, increasing functions. If you graph those things, they go up to the right. Okay, whereas fractional bases, like this 1/3 one, are decreasing functions or decaying functions. They'd be going down to the right, getting smaller and smaller over time. Okay, there are a bunch of properties that we should know about. And these are on your sheet, so just read them over and see if they make sense. But okay, there are 7 of them we're going to talk about. Okay. A horizontal asymptote is the first one. All exponential functions approach but never cross a horizontal line. And by that I mean, if I had some sort of function that say went down like this, they're going to get closer and closer and closer to this imaginary horizontal line down here, but they never actually touch it. Okay. Or increasing, they start at a horizontal line and start going up, but they never actually touch that imaginary line at the bottom there. Okay. Our standard horizontal asymptote is the x-axis, which has the equation y equals 0. And we're going to look at some graphs in a second, but just to get the idea of the properties. Okay, all graphs have steepness. Okay, for an increasing function, that'd be one of these ones on the right here, or sorry, on the left. The larger the base, the steeper the increase. So for example, 2 to the x and 5 to the x, well 5 is obviously bigger than 2, it would be increasing, it would be steeper. So it would grow really fast, whereas this one might grow a little slower. Okay. For decreasing functions, the smaller the fraction, so if it was 1/5 compared to 1/2, 1/5 would be steeper because it's a smaller number. Okay, so basically, the bigger the base, right, the steeper the thing goes. Our y-intercept, it's always okay at the point where x equals 0. We know that from polynomials. That hasn't changed. Okay, the x-intercept, that's something we have to talk about. It's kind of tricky. It's almost like a trick question because exponential functions don't have zeros. Okay, they come down to, but they never touch the x-axis. Okay, they get closer and closer to it, that horizontal asymptote idea, so they don't actually have any zeros. Exponential functions, their domain is always all real numbers. Okay, that won't change. These things go left and right forever and ever and ever. Our range, okay, it depends on our horizontal asymptote. Okay, but generally it's going to be y is greater than 0. Why is that? Well, that's our horizontal asymptote normally. And again, remember our objective is we come down to, but we never touch it. That's why there's no equal sign right here, just a greater than sign. And we generally want a couple points. So to find other points, we can substitute any x value you want to into the equation and calculate y. The easiest point, if you put in x equals 1, remember our equation is b to the power of x. Well, if x is 1, we get b to the power of 1, or in other words, we get the value b for y. Okay, as I said, we'll go through a couple examples here to get an idea how this works. But those are the kind of properties we should recognize. Okay, here's our graph. Let's figure out its properties. So property number 1 was our horizontal asymptote. The imaginary line we approach, but we don't cross. I'm going to call that HA for horizontal asymptote. What do we approach but don't cross? Well, that would be this line right down here, right? We're getting closer and closer to it, but we're never touching it. Its equation is y equals 0, the x-axis. Okay, property number 2, we were talking about steepness. Well, okay, it's hard to say in comparison to something, but we definitely know this is a increasing function. Remember, it's always from left to right. Okay, property number 3 we had on the last page, or up top for you guys. The y-intercept. It's the point where x equals 0. Where does x equal 0? That would be right here. What's that y value? In this case, it's 1. Okay, property 4. Are there any x-intercepts? No, there's no x-intercepts. We said there shouldn't be any because it doesn't hit the x-axis, right? It approaches it, doesn't cross it. Okay, property number 5 we had talked about was the domain. Looking at our graph, you can hopefully see this graph goes left and right forever. Now it's hard to talk about the right side, but this graph would keep getting wider and wider and wider, 2 and something, 3 and something, 4 and something. The graph at the top would keep going up like that, right? It's going to get wider and wider and wider over time. It just doesn't show on our graph at this point. Our range, it's all real numbers. Specifically, well, it's from, how do I show this right here? From this red line right here up, right? But it doesn't actually hit the red line, that horizontal asymptote. So we say it gets as low as 0, but it doesn't actually hit it. So no equal sign there. And it's got to be greater than that value at all times. Okay, and then property number 7. Oh, it's finding another point, but it doesn't really make sense finding a point you can see on the graph. So the second part of this question was identify its properties. We did that. What might its equation be? Well, there's where the other point comes in handy. So our base. What is our base? Kind of hard to guess, but based on that second point I said a second ago, 1 and b, which in our case is 1 and 5, kind of a hint that b is 5. So our equation would be 5 to the x. Okay, so that's how we can recognize some properties. We can look at this thing, we can figure out its equation, identify some interesting things about the equation and the graph, and we want to start working with them a little bit. Okay, so let's take a look at these things. So based on the same idea, without looking at a picture this time, can we figure out some of the same properties? Is this going to be increasing or decreasing? How do I tell? Well, my base tells me whole numbers are increasing. Okay. Fractions decreasing. The y-intercept. We know for the y-intercept, x is always, always, always 0. So if I were to put in 0 into my equation, I'll get f at 0 equals 6 to the power of 0. What's anything to the power of 0? 1. There's my y-intercept. If I do the same thing over here, f at 0. Well, 1/5 to the power of 0. Anything to the power of 0 equals 1. So as I was saying, our y-intercept is generally 1. The horizontal asymptote. The horizontal asymptote for our purposes is the x-axis. So y equals 0 and y equals 0. There is 1 or 2 little tricks that can come up with that, but we're not going to worry about those right now. Our domain, all real numbers, goes left and right forever and ever and ever. So all real numbers, left and right, ever and ever and ever. Our asymptote, our range depends on our asymptote, so we know it's going to be greater than 0. It doesn't hit that asymptote. Same thing over here. And another point. So let's pick a nice value. If I said x was 1, I'd get f at 1 would be 6 to the power of 1. So what's another point? 1 and 6. If I did the same thing over here, another point would be 1. And if I put 1 into that equation, I get 1/5. Okay, so we can figure out some properties based on our equations. And the ones that don't change for us right now, our y-intercept is always going to be 1. Our asymptote is always going to be 0. Okay. Always going to be all real numbers. And our range is going to be always greater than 0. And notice that was the same for these ones. Right, that's for our purposes right now. We're going to start with that. Okay. Okay, what can we do next? Okay, we want to sketch the graph of an increasing exponential function that has a domain of all real numbers, a range greater than 0, and a y-intercept of 12. So let's do this in order here. Increasing function. What does that tell me? My base has to be greater than 1. It's going to be a whole number. And it's got to go up to the right. Okay, a domain of all real numbers. So that's normal. A range greater than 0. That's normal. And a y-intercept of 12. Okay, so my y-intercept is 12, which means it's a point 0 and 12. So the only really important things are here is that I put a 12 for my y-intercept, and then make my graph grow to the right. So it's got to be going up to the right, and it's going to approach but never actually hit the x-axis. There's an increasing function. Is that the only one? For sure not. Maybe I wanted to say mine goes, oh, it's going to grow steeper this time. That would work. Or I could have one that goes even less steep, right? It takes forever to go. As long as it goes through 12 and it's increasing, it's going to have a domain of all real numbers, and a range greater than 0. So lots and lots of options here. They just said a graph, didn't tell us the graph. Okay, let's find the equation of this graph now. Let's work backwards. So what do I recognize? I recognize, well, it's decreasing. I recognize I got a y-intercept. Ooh, that's a hard one. It's a weird dot there, right? It's not in a nice spot for us. So how can I figure out the y-intercept if I don't have this nice dot? We said our y-intercept is always going to be 1. Maybe it's 1. It's hard to read on the scale a little bit here. So let's take a look at the values we do have. What do I notice about these values? Okay, 3 and 9. Well, those are multiples of each other, and in fact, they're multiples of 3. So if I were to stop and think for a second, I want to make an equation. We know our equation is going to be in the form b to the power of x. All I really need is the b part. It's got to be a decreasing function, which means it has to be a fraction. And what number would make sense to put in the bottom there? The fact that these are factors of 3. Well, let's see if I can just put a 3 down there. I'll put in brackets, okay, to make sure it's the whole base. Let's try this. If I took 1/3 and put it to the power of 1, or sorry, negative 1, because that's my first x over here, right? F at negative 1 would give me this, right? Let's see if it works. What happens to negative exponents? Just to flip them over. So that becomes 3 to the... Hey, that is a point on my graph, negative 1 and 3. That seems to work. What if I tried the next one? F at negative 2. F at negative 2 would give me 1/3 to the negative 2, which means I'd have to flip it, which means I'd get 9. And sure enough, negative 2 and 9 is a point. So the things that really matter are the fact that it was decreasing and the fact that I recognize my base had 3's in it, or factors of 3's in it. Okay. Decreasing told me fraction. The numbers in my graph told me the fact that there are 3's on the bottom of that fraction. Okay. Okay, at times we're going to have a slightly different equation. Not very often for us, but at times we could have this. Okay, where we put a number in front of the base. So y equals a times b to the x. When that happens, a causes our graph to be stretched or compressed in the vertical direction. Okay, now it's kind of hard to visualize, but instead of having a function that looks like this, maybe it's the same function, but it's been stretched. It goes up a lot faster right off the bat, and it's been stretched vertically. When that happens, the only big difference is that our y-intercept will now become the value of a, and the reason why is, if I were to choose f at 0, because we know our our y-intercept is x equals 0, we'll get a times b to the power of 0, right? Well, what's b to the power of 0? That's 1. And a times 1 gives me a. So when I put in value out front, it changes my y-intercept. Okay? That's really the only difference. Okay? And most applications, this is our initial value, our starting point. Because at time 0, we get the value a. Okay, so let's take a look at this one version here. We can try this. Hey, the horizontal asymptote, that is not going to change for us. Horizontal asymptote, still y equals 0. Our y-intercept, well, let's see what happens when x is 0. Now, I put in 5 times 1/2 to the power of 0. Half to the 0 is just the value of 1. So my y-intercept is 5. My initial value is 5, which I can look at the equation and tell that, but I also proved it mathematically. Okay. And actually, I just wanted to sketch this. Forgot to do that part. So let's make a sketch. Okay, make a sketch. We choose numbers in a table, like normal. And the equation was 5, back up here for a second, 5 times 1/2 to the x. Okay, to figure out the y's, I'm going to put these values of x in. I already did this one down here. We said this was 5, right? So let's try 5 times 1/2 to the negative 2. We know when we get a fraction that's negative, we're supposed to flip it. So that's like saying 2 squared, so 5 times 4. That gives me 20. Now you can use your calculator, it works just the same. Okay, we try the next one. 5 times 1/2 to the negative 1. 5 times 2, flip it over, becomes 1. 5 times 2 is 10. There's a pattern happening here, right? 20, then 10, then 5. What's happening? It's cutting in half each time. Okay, which makes sense because my base is 1/2 each time. So our graph, I can't really fit negative 2 and 20 on there. Don't worry about it. Negative 1, 10 we'll say is way up there. 0 and 5, 1, 2, 3, 4, 5, 1 and 2.5, okay, 1 and a quarter, right there. There's my graph, okay. And the domain range, obviously you can see all real numbers and greater than 0, like normal.